welcome to this problem walkthrough. Today, we are tackling LeetCode problem number 1827, minimum operations to make the array increasing. In this problem, we focus on modifying an array with the minimum operations needed to make it strictly increasing. Let's dive in and explore the solution step by step. This problem, LeetCode number 1827, is about making an array strictly increasing with the minimum number of operations. You're given an integer array nums, and in one operation, you can increment any element in the array by 1. The goal is to determine the smallest number of these operations needed to make the array strictly increasing. A strictly increasing array means that for every index I, the value at nums, I, must be less than the value at nums, I plus 1. For example, 1, 2, 3 is strictly increasing, but 1, 1, 2 is not. Arrays of length 1 are automatically considered strictly increasing because there's no comparison to be made. The input consists of the array nums, or its length can range from 1 to 5,000, and each element falls between 1 and 10,000. The output is a single integer, which represents the minimum number of operations required to meet this condition. Let's look at an example to better understand the problem. Suppose the input array is nums equals 1, 1, 1. Here, the array is not strictly increasing because nums, 0, is equal to nums, 1, and nums, 1, is also equal to nums, 2. To fix this, we increment nums, 1, by 1, making it 2. Now the array becomes 1, 2, 1. However, the last element, nums, 2, is still less than or equal to nums, 1. So, we increment nums, 2, by 1 to make it 2, resulting in 1, 2, 2. Since this still doesn't satisfy the strictly increasing condition, we increment nums, 2, again to make it 3. Now the array becomes 1, 2, 3, which is strictly increasing. The total number of operations required here is 3. This example demonstrates the need to carefully adjust each element to ensure the array satisfies the condition. Now consider another example with the input nums equals 1, 5, 2, 4, 1. Here, the array is not strictly increasing because several elements violate the condition. First, nums 2 is less than nums 1, so we increment nums 2 by 4 to make it 6. The array becomes 1, 5, 6, 4, 1. Next, nums 3 is less than nums 2, so we increment nums 3 by 3 to make it 7. The array now becomes 1, 5, 6, 7, 1. Finally, nums 4 is less than nums 3, so we increment nums 4 by 8 to make it 8. The array becomes 1, 5, 6, 7, 8, which is now strictly increasing. The total number of operations in this case is 4 plus 3 plus 8 equals 14. This example shows how multiple adjustments may be needed for different elements in the array. In contrast, consider the input nums equals 8. Here, the array has only one element, so it's already strictly increasing by definition. No operations are needed, and the output is 0. This demonstrates that arrays of length 1 are always valid. To summarize, the constraints require handling arrays with up to 5,000 elements and values as large as 10,000. Efficient solutions are crucial to manage these large inputs within time limits. Edge cases include arrays that are already strictly increasing, arrays of length 1, and arrays where all elements are the same. In such cases, careful adjustments are necessary to ensure efficiency and correctness. To solve problem number 1827, the task is to determine the minimum number of operations required to make the given array strictly increasing. In this context, an operation allows us to increment any element of the array by 1. One possible approach to solving this problem is the brute force method. The intuition here is simple. For each element in the array, we ensure that it satisfies the strictly increasing condition, which means nums I must be greater than nums I1 for all indices greater than 0. If this condition isn't met, we calculate how much nums I needs to be incremented to restore the property. The process involves traversing the array, identifying violations of the strictly increasing condition, and incrementing the elements as needed, while keeping track of the number of operations performed. By the end of the traversal, the array will meet the required condition, and we'll have our answer in terms of the total operations performed. The brute force approach has a clear complexity profile. It runs in O, n, time, where n is the length of the array, because we process each element exactly once. The space complexity is O(1), as the solution is implemented in place without requiring additional memory. This makes it an efficient solution in terms of both time and space. However, this approach does assume that modifying the array directly is acceptable. While this is optimal for most scenarios, it might not be suitable if the original array needs to remain unaltered. Despite this, the simplicity and efficiency of this method make it a strong candidate for solving the problem in a straightforward manner. Given the considerations, the chosen strategy for this problem is an optimized iterative approach, which is essentially the brute force method we discussed with slight refinements. The key insight here is that at each step, we only need to compare the current element with the previous one. If the current element is already greater than the previous, no action is needed. However, if it isn't, then we calculate the exact number of increments required to make the current element 1 greater than the previous. This ensures that the strictly increasing condition is satisfied. The elegance of this approach lies in its simplicity. By iteratively addressing each violation as it occurs, we avoid the need to revisit earlier elements of the array. The method is efficient, running in linear time, and ensures that every operation performed directly contributes to solving the problem. This iterative approach has an optimal complexity profile, running in O(n) time and using O(1) space. It is both efficient and straightforward to implement. Compared to other potential strategies, this method stands out for its practicality. Recursive or more complex greedy approaches, for example, would introduce unnecessary computational overhead and complicate the implementation, despite leading to the same result. In contrast, the iterative solution is clean and concise. Furthermore, since it modifies the array in place, it avoids the overhead of creating and managing additional data structures. However, this in-place modification could be a limitation in scenarios where the original array must remain unchanged. In such cases, we could create a copy of the array to work with, but this would increase the space complexity to O(n). Overall, the iterative approach is the best choice given the constraints and simplicity of the problem. The iterative solution effectively balances simplicity, efficiency, and practicality, making it the ideal approach for this problem. It capitalizes on the straightforward nature of the strictly increasing condition, ensuring a clean and optimal implementation. With its linear time complexity and constant space usage, it addresses the problem in the most resource-efficient manner possible. This approach is easy to understand, implement, and adapt, making it well-suited for scenarios where performance and clarity are priorities. By focusing on the key insight of fixing violations in a single pass, this solution demonstrates how a seemingly complex problem can be tackled with an elegant and simple strategy. In this problem, we are tasked with making a given array strictly increasing using the minimum number of operations. A strictly increasing array means that every element at index I must be less than the element at index I plus 1. The operation allowed is to increment any element of the array by 1. To solve this efficiently, we'll use a greedy approach that processes the array in one pass, giving us a time complexity of O(n). The key idea is to adjust each element only when necessary to maintain the strictly increasing condition, while minimizing the number of increments. To start, we initialize two variables, operations, which will track the total number of increments needed, and previous, which keeps track of the previous element's value as we traverse the array. Initially, previous is set to the first element of the array. This setup allows us to compare each subsequent element to previous and determine the necessary adjustments dynamically. Now, we proceed by traversing the array starting from the second element, at index 1. For each element, we check whether it is greater than the value stored in previous. If it is, no adjustments are needed, and we simply update previous to the current element's value. However, if the current element is less than or equal to previous, we calculate the minimum increment needed to make it strictly greater. This increment is given by previous I plus 1. We add this increment to our operations counter, which keeps track of all adjustments made so far. After incrementing the current element, we update previous to reflect its new value, ensuring that it remains valid for subsequent comparisons. Once the traversal is complete, the total number of operations required to make the array strictly increasing is stored in the operations variable, which we return as the result. The greedy approach works efficiently because we process the array incrementally, making the necessary adjustments locally at each step. By ensuring that each element satisfies the strictly increasing condition relative to the previous one, we guarantee that the array as a whole will meet the requirement, minimizing the number of operations globally. Another advantage of this approach is its use of constant space. We only maintain two variables, operations to count the increments and previous to track the previous element's value. This makes the algorithm both time and space efficient. It's also important to consider edge cases. For instance, if the array contains only one element, no operations are needed since it's already strictly increasing. In cases where all elements are equal, every element after the first must be incremented to maintain strict inequality, leading to predictable results. Similarly, if the array is strictly decreasing, every element after the first will need to be incremented to exceed the previous one, resulting in cumulative adjustments. The algorithm makes use of only the input array and two additional variables. The input array is processed directly during traversal, while operations keeps track of the total number of increments, and previous helps ensure the strictly increasing condition is met. The efficiency of the algorithm lies in its complexity. The time complexity is O(n), because we traverse the array exactly once. The space complexity is O(1), since we use only a constant amount of extra space. This balance of time and space efficiency makes the solution well suited for large inputs, as it avoids unnecessary computations and additional memory usage. Let's walk through an example to solidify our understanding. Consider the input array A equals 1, 1, 1. We begin by initializing operations to 0 and previous to the first element, which is 1. Starting at index 1, we see that A1 equals 1, which is not greater than previous. To make it strictly greater, we increment A1 by previous A1 plus 1, which is 1. This makes A1 equal to 2, and we update previous to 2 while adding 1 to operations. Moving to index 2, A2 equals 1, which again is not greater than previous. We increment A2 by previous A2 plus 1, which is 2. Now, A2 becomes 3, previous is updated to 3, and we add 2 to operations. The traversal is complete, and the total operations required are 3. This example demonstrates how the algorithm ensures the array becomes strictly increasing with the minimum number of adjustments. Additionally, since the problem only requires increments, we don't modify the input array itself. Instead, we simulate these changes using previous, ensuring optimal performance. This Python implementation solves LeetCode problem number 1827, minimum operations to make the array increasing. The problem requires transforming the input array into a strictly increasing sequence using the minimum number of increment operations. Here's how the algorithm works step by step. 1. Initialization. We start by initializing a variable operations to 0. This will store the total number of increment operations required. 2. Iterating through the array. We loop through the array starting from the second element, index 1, because we compare each element with its previous one. 3. Checking the strictly increasing condition. For each element at index I, we check whether it is less than or equal to the previous element, nums, I1. If it is, the array is not strictly increasing at this point. For calculating the required increment, to fix this, we calculate the amount by which the current element, nums, I, needs to be increased. This is given by nums, I1, plus 1 nums, I, ensuring that nums, I, becomes just greater than nums, I1. 5. Updating the current element, we increment the value of nums, I, by the calculated amount to make it strictly greater than the previous element. 6. Updating the operations count, we add the increment value to the operations counter to keep track of the total number of operations performed. 7. Returning the result, after processing all elements, the final value of operations is returned as the result. Example walkthrough. Consider the input array nums equals 1, 1, 1. Start with operations equals 0. At index 1, nums, 1, 1, is not greater than nums, 0, 1. Increment nums, 1, by 1. Now nums equals 1, 2, 1, and operations equals 1. At index 2, nums, 2, 1, is not greater than nums, 1, 2. Increment nums, 2, by 2. Now nums equals 1, 2, 3, and operations equals 3. Return operations equals 3. This approach is efficient with O(n) time complexity, as we iterate through the array once, and O(1) space complexity, as no extra data structures are used. This is the Java implementation of LeetCode problem number 1827, minimum operations to make the array increasing. The code mirrors the logic of the provided Python implementation, utilizing a for loop to iterate through the array and calculate the minimum number of operations required to ensure each element is strictly greater than the previous one. Key differences include explicit type declarations for variables and the use of Java syntax for array handling. The solution maintains the same time complexity of O(n). To solve this problem, let's start with the example where nums equals 1, 1, 1. Initially, the input array is 1, 1, 1, and the operations counter is set to 0. First, we process the element at index 1. Here, nums 1 equals 1, which is not greater than nums 0, also 1. To make nums 1 greater, we calculate the increment needed as nums 0 plus 1 minus nums 1, which gives 1. We then update nums 1 to 2 by adding the increment, and the operations counter is updated to 1. The array now becomes 1, 2, 1. Next, we process the element at index 2. Since nums 2, which is 1, is less than or equal to nums 1, which is 2, we calculate the increment needed. This time, the increment is nums 1 plus 1 minus nums 2, resulting in 2. We update nums 2 to 3 and add 2 to the operations counter, bringing the total operations to 3. The final array state becomes 1, 2, 3. The total number of operations needed for the first example is 3. Now, let's look at the second example where nums equals 5, 3, 4, 2, 6. Initially, the input array is 5, 3, 4, 2, 6, and the operations counter is again set to 0. First, we process index 1. Here, nums 1 is 3, which is less than nums 0, which is 5. To fix this, we calculate the increment as nums 0 plus 1 minus nums 1, which equals 3. We update nums 1 to 6, and the operations counter becomes 3. The array now looks like 5, 6, 4, 2, 6. Now, moving to index 2, nums 2 is 4, which is less than or equal to nums 1, which is 6. The increment required is nums 1 plus 1 minus nums 2, which is 3. We update nums 2 to 7, and the operations counter increases to 6. The array state is now 5, 6, 7, 2, 6. At index 3, nums 3 is 2, which is less than nums 2, which is 7. The increment here is nums 2 plus 1 minus nums 3, resulting in 6. We update nums 3 to 8, and the operations counter becomes 12. The array updates to 5, 6, 7, 8, 6. Next, we process index 4. Nums 4 is 6, which is less than or equal to nums 3, which is 8. The increment required is nums 3 plus 1 minus nums 4, which gives 3. We update nums 4 to 9, and the operations counter increases to 15. The final array state becomes 5, 6, 7, 8, 9. Therefore, the total number of operations needed for this example is 15. Let's consider the third example, where nums equals 8, 8, 8, 8. Initially, the input array is 8, 8, 8, 8, and the operations counter starts at 0. First, we process index 1. Here, nums 1 is 8, which is not greater than nums 0, also 8. The increment needed is nums 0 plus 1 minus nums 1, which equals 1. We update nums 1 to 9, and the operations counter becomes 1. The array now looks like 8, 9, 8, 8. At index 2, nums 2 is 8, which is less than nums 1, which is 9. The increment required is nums 1 plus 1 minus nums 2, which results in 2. We update nums 2 to 10, and the operations counter increases to 3. The updated array is 8, 9, 10, 8. Finally, we process index 3. Nums 3 is 8, which is less than or equal to nums 2, which is 10. The increment required is nums 2 plus 1 minus nums 3, which equals 3. We update nums 3 to 11 and the operations counter increases to 6. The final array state becomes 8, 9, 10, 11. The total number of operations required for this example is 6. The time complexity of this solution is O, n, where n represents the length of the input array. This is because the algorithm processes the array in a single loop, starting from the second element and iterating through to the last. In each iteration, a few constant time operations are performed. These include a comparison to check if the current element is less than or equal to the previous one, a calculation to determine the increment value if an adjustment is needed, updating the current element, and incrementing the operations counter. All of these are O(1) operations. Since the loop runs n1 times, the overall time complexity becomes O(n1) O(1), which simplifies to O(n). In the best-case scenario where the array is already strictly increasing, no adjustments are needed, but the algorithm still iterates through the entire array once, so the time complexity remains O(n). In the worst-case scenario, every element in the array may need an adjustment. For instance, if all the elements are the same, the algorithm still performs one comparison and adjustment per element after the first. Despite this, the loop only runs n1 times, and each iteration involves constant time operations. This means that even in the worst case, the time complexity is still O(n). Now, looking at space complexity, the solution operates in O(1) space. This is because it modifies the input array directly instead of using additional data structures. The only extra space used is for two variables, one to store the total count of operations and another as a temporary variable for increment calculations. Since these do not scale with the size of the input array, the space complexity remains constant at O(1). To better understand the efficiency of this approach, let's compare it with a brute force method. A naive solution could involve repeatedly scanning the array to check if it is strictly increasing and adjusting elements whenever needed. This would require nested loops, where the outer loop iterates through the array and the inner loop resolves discrepancies. In the worst case, this results in a time complexity of O(n², which is significantly less efficient. On the other hand, the optimized solution processes each element in a single pass, performing adjustments immediately. This eliminates the need for repeated scans, reducing the time complexity to O(n). Mathematically, this is because the loop runs n1 times, and each iteration consists of constant time operations like comparisons, arithmetic, and assignments. Thus, the total number of operations is directly proportional to n. Additionally, since no extra memory is used beyond the two variables, the space complexity remains O(1). To summarize, the solution achieves a time complexity of O(n) and a space complexity of O(1). Its single-pass design makes it far more efficient than a brute force approach, particularly for larger arrays. By processing each element exactly once and making adjustments in place, the algorithm minimizes both time and space usage, making it a practical and scalable solution for this problem. When approaching this problem, there are several common mistakes that can trip you up if you're not careful. First, failing to handle edge cases can lead to unnecessary computations or even incorrect outputs. For example, if the array is already strictly increasing, like 1, 2, 3, no operations are needed. But failing to account for this might result in overcomplicating your solution. Another mistake is modifying the array incorrectly, such as decrementing elements instead of incrementing. Remember, the problem explicitly requires that you can only increase elements. Overcomplicating the solution is another pitfall. Some approaches use nested loops or extra data structures, which unnecessarily increase time complexity. A single pass through the array is sufficient to achieve an optimal O(n) solution. Additionally, incorrect increment calculations can lead to off-by-one errors. For example, you need to ensure that each element is increment to I1 plus 1, not just to match its predecessor. Lastly, ignoring input size constraints can cause performance issues. Since the input size can go up to 10 to the power of 5, any solution with O(n²) complexity will likely fail due to time limits. A linear solution is not just optimal but essential for passing all test cases. Now, let's look at some key insights that can help you tackle this problem effectively, especially in an interview setting. One critical observation is focusing on the relationship between adjacent elements. For any element I, it needs to be at least I1, plus 1 to maintain the strictly increasing condition. Keeping this relationship in mind simplifies the logic significantly. This leads us to an optimization pattern, solving the problem in a single traversal by maintaining the invariant that each element satisfies the condition. This is a great example of a greedy algorithm. It minimizes operations while ensuring correctness, making it both simple and efficient. When explaining your solution in an interview, emphasize the O-N approach. Highlight its efficiency and how it avoids unnecessary operations by directly calculating the required increments. Be prepared for follow-up variations as well. For instance, an interviewer might ask how you'd handle scenarios where decrements are allowed or where the goal is to minimize total modifications rather than just increments. These variations could demand different strategies, so it's good to have a flexible mindset. This problem also has connections to other related problems, which can help deepen your understanding. For instance, in LeetCode 665, you modify at most one element to make the array non-decreasing. Or in LeetCode 941, you check if the array follows a specific increasing and decreasing pattern, like a mountain. Another example is LeetCode 2064, which involves incremental adjustments in a greedy context. Finally, LeetCode 1007 challenges you to calculate the minimum operations needed to achieve a desired condition by rotating dominoes. Thinking about these related problems can give you a broader perspective. Now, in terms of alternative approaches, one straightforward but inefficient method is brute force. Here, for every element, you increment until the strictly increasing condition is satisfied. While this works, it's O(n squared), complexity is impractical for large inputs. The optimal greedy approach, on the other hand, makes a single pass through the array. As you compare each element with the previous one, if I is less than or equal to I1, you calculate the exact difference needed and increment I directly. This ensures O(n) time complexity and minimizes operations. However, it is worth noting the trade-offs. While the greedy approach is perfect for this version of the problem, if the constraints change to allow decrements or other operations, you may need to explore dynamic programming or more elaborate techniques to adapt your solution. Great job! We've covered how to solve this problem efficiently using a greedy approach. Remember, practicing similar problems will help solidify these concepts. Thank you for watching, and don't forget to like, share, and subscribe for more tutorials. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!